Ever feel like you're just drowning in technical documents?
Mhm.
Trying to get your head around some complex field, but you just don't have months to study it.
Oh, absolutely. Happens all the time.
You're definitely not alone. So, welcome to the Deep Dive, the show where we try to, well, cut through that noise and give you the core ideas behind tricky topics.
That's the goal.
And today, we've got a really interesting stack of material from a listener. It's all focused on something called Smooth Particle Hydrodynamics, SPH for short.
Right. SPH. It's a big one in computational mechanics.
Yeah, we've got a PhD thesis here from Swansea, a couple of papers from computational particle mechanics, another from computer methods in applied mechanics and engineering. Quite a bit to dig into.
A good mix of sources then. Thesis and papers.
Exactly. And our mission really is simple. Pull out the main ideas, what SPH is good for, what the challenges are.
Get the essence of it.
Get the essence, yeah, exactly. Give you a solid grasp of why it's important for simulating physical stuff without needing a PhD yourself.
Sounds like a plan. Where should we start?
Okay, let's just jump right in. What is SPH? Why should we, care about this method?
Well, what's really cool about SPH right off the bat is that it kind of throws out the traditional way we think about simulating materials.
How so?
For ages, most methods used a mesh, like a grid of interconnected points or elements to represent, say, a chunk of metal or even a fluid.
Right, the standard finite element approach, for example.
Exactly. SPH is totally different. It's meshless or mesh-free. Instead of a grid, it uses a whole bunch of individual particles.
Wow.
Think of them like tiny, tiny dots that together represent the continuous material.
Okay, particles instead of a grid. No mesh. What's the big win there? Why bother changing the approach?
The main reason really driving these meshless methods is to get around some, let's say, inherent problems with meshes.
Okay, like what?
Imagine simulating something getting really, really deformed, like a piece of metal being smashed or stretched way out. With a mesh, those grid elements can get super distorted, right? Squashed flat or stretched thin. And when that happens, your calculations can go haywire. You lose accuracy.
Ah, okay. The grid itself breaks down, essentially.
Precisely. SPH, because it just uses particles that can move freely, handles these huge shape changes much more gracefully. The particles just rearrange themselves, so it naturally avoids those mesh distortion headaches.
That makes sense. So it's better for simulating really extreme events, maybe.
That's a huge part of its appeal, yeah. Where traditional methods might struggle or even fail.
And I guess maybe setting up the simulation is easier. You don't have to build that complicated mesh in the first place.
That's another big plus they mention in the research. Generating a good mesh, especially for complex shapes, can be a real pain. It takes time, expertise.
Right.
With SPH, distributing the particles is often, though not always, simpler. And it potentially integrates a bit better with, CAD models. So yeah, less complex pre-processing is a definite advantage.
Okay, so we get the what meshless particles and the why avoids mesh distortion, potentially simpler setup. How does it actually work? How do these particles, talk to each other to simulate a solid or a liquid?
Good question. They're not just independent points floating around. The magic is in how they interact locally.
Locally?
Yeah. Each particle carries information, its mass, its velocity, maybe its stress state, things like that. SPH uses a clever trick to sort of smooth or average these properties over a small neighborhood of nearby particles.
Smooth them out. How?
It uses something called a kernel function.
A kernel function. Okay, what's that?
Think of each particle having a little sphere of influence around it. The kernel function basically defines the size of that sphere and, crucially, how much influence particles inside that sphere have on the central one.
Ah, so closer particles have more influence.
Exactly. Particles right nearby have a strong effect, while particles further out near the edge of the sphere have less influence. It's a weighted average, essentially.
Okay. And you mentioned interacting.
Right. There are kind of two steps happening constantly. First, a particle gathers information from all its neighbors within that sphere of influence. Then, based on what it gathered, it scatters its own influence back out to those neighbors.
Gather and scatter, like a constant local check-in.
You got it. That's how the properties get shared and updated across the whole collection of particles.
Now, the thesis mentioned something. Sounded a bit complex. Anisotropic changes in particle spacing? And anisotropic compact supports. What's that about?
Okay, yeah, this is where it gets a bit more advanced, but it's important for accuracy, especially in solids undergoing big deformations.
Right.
Imagine you stretch a material way out in one direction and squash it in another. Your initially nice, evenly spaced particles, they're going to get spread far apart in the stretching direction and crammed together in the squash direction. That's anisotropic spacing uneven.
Okay, makes sense.
Now, if your particle's sphere of influence, that kernel, stays perfectly round, it might end up grabbing information from way too many neighbors in the squash direction and hardly any in the stretch direction. That biases the calculation.
Ah, so the sphere needs to adapt.
Exactly. Anisotropic compact supports are basically kernel shapes that can deform. They can stretch or squash along with the particle spacing, so the particle maintains a more balanced neighborhood even when things get really distorted. It's like its little influence cloud reshapes itself.
Adaptable influence clouds. That's pretty clever.
It's crucial for handling large strains accurately.
The research also mentioned pullback and push-forward operations and kernel and gradient corrections. Sounds like a lot of mathematical footwork to keep things accurate.
It is. Think about it. As the material deforms, you're constantly relating its current shape back to some original or reference shape. Pull back and push forward are the mathematical tools to consistently translate things like the kernel function itself or its rate of change, the gradient between these different states, the current state, and the reference state.
So it's about keeping your measurements consistent as everything moves and stretches.
Pretty much. And then the kernel and gradient corrections, those are further refinements. They help ensure the SPH approximation is accurate enough that it meets certain mathematical criteria. They talk about achieving completeness.
Completeness.
Yeah, it basically means the method can perfectly reproduce simple things like a constant velocity field or a linear stress field. If it can't even get those simple cases right, you can't really trust it for complex stuff. So these corrections are vital for accuracy.
Got it. Lots of careful adjustments needed. Okay, so we have particles, kernels, corrections. Now, the thesis talked a lot about different Lagrangian formulations. What does that mean in this context?
Right, Lagrangian formulations. This is about the fundamental perspective you take when describing the motion. In a Lagrangian approach, your viewpoint, your sort of computational grid, even though SPH is meshless, your frame of reference moves with the material.
Okay, so you're following the particles along.
You're following the material points, yeah.
Yeah.
Imagine tagging a specific speck of dust within a flowing fluid. You track that speck. That's the Lagrangian idea. Now, within SPH, there are different ways to set up the math based on this idea. The thesis digs into three main ones. Total Lagrangian.
TLF.
Yep, TLF. Then updated Lagrangian formulation, ULF, and updated reference Lagrangian, URL.
Total updated reference. What's the core difference between them? How do they track the material differently?
It's all about the reference configuration. What shape are you comparing the current state back to?
Okay.
In total Lagrangian TLF, everything, equations, stresses, strains, is always referred back to the original undeformed shape, the starting point, like using the original blueprint for everything.
Always back to the beginning.
Right. Updated Lagrangian, ULF, is the opposite. It constantly updates its reference. At every single time step in the simulation, the current deformed shape becomes the reference for calculating the next tiny step.
So it's always looking just one step back.
Exactly. Like redrawing your map constantly based on where you are right now.
And the third one? Updated reference.
URL is kind of a hybrid. It uses an intermediate reference configuration that gets updated, but maybe not every single step. It gives you more flexibility. You can choose how often to update this reference frame.
Okay, so it's more flexible.
And the thesis, specifically, introduces and tests a new URL SPH framework. They designed it to be really robust, especially for fast-moving solids, things involving heat, even fracture.
Ah, so their contribution was this new URL approach.
Yeah, a key part of it. Their goal was to make something versatile that could, if needed, behave like a pure TLF or a pure ULF, giving the user more options depending on the problem.
Interesting. A sort of adaptable framework. Now, whichever formulation you pick, TLF, ULF, URL, SPH, still has to obey basic physics, right? The sources mention conservation laws.
Oh, absolutely. That's non-negotiable for any serious simulation method. SPH has to respect the fundamental laws of physics.
Why?
Well, the big ones. Conservation of linear momentum, basically. Things keep moving unless a force acts on them. Conservation of angular momentum, the same idea, but for rotation. And conservation of energy. Energy isn't created or destroyed, just changed from one form to another.
The big three, yeah. How does SPH actually, encode these laws? what variables are involved?
It uses specific mathematical quantities. For momentum, you track things like velocity and momentum density for each particle. To describe the deformation, the shape change, a key variable is the deformation gradient tensor, usually called F.
Okay.
It mathematically captures how a tiny bit of material stretches or rotates. Related to that are things like the area map H and volume map J, tracking how areas and volumes change. And then for the internal forces, you use stress tensors.
Like Cauchy stress.
Yeah, Cauchy stress measures force on the current deformed area. There are others too, like Piola-Kirchhoff stresses, which relate forces back to the original undeformed area. Depends on the formulation, TLF or ULF.
So the choice of Lagrangian formulation influences which stress measure you use.
It often does, yes. The different papers and the thesis explore various ways to write down and implement these conservation laws using these kinds of variables, sometimes breaking down the deformation into smaller, incremental steps relative to a reference state.
Okay, so it's grounded in fundamental physics, tracked using specific variables tailored to the particle approach. Now, the million-dollar question for any simulation: how reliable is it? Is it stable? Is it accurate? I think you mentioned earlier SPH had some known issues.
Yeah, that's a critical point. Classic early SPH did have some well-known problems. One was called tensile instability.
Tensile instability, what's that?
Under tension, when you're stretching the material, the particles could sometimes just clump together in weird non-physical ways. It messed up the results.
That doesn't sound good.
Not at all. But the good news, as the thesis notes, is that using these Lagrangian formulations, particularly TLF, inherently helps to reduce or even eliminate that specific problem.
Okay, so the framework itself helps there. But what about, you also mentioned spurious pressure oscillations.
Right. That's another classic issue. You can get these weird non-physical wiggles or spikes in the calculated pressure, especially when simulating fluids or nearly incompressible materials. They aren't real, just artifacts of the numerical method.
So how do you get rid of those?
Researchers developed various stabilization techniques. The papers we looked at mentioned things like Riemann-based upwinding or something called SUPG Streamline Upwind Petrov Galerkin.
Whoa, OSUPG, sounds fancy.
Yeah, the names get a bit intense. But the basic idea behind these methods is to introduce a tiny, controlled amount of numerical dissipation.
Dissipation, like friction.
Sort of, yeah. Think of it as adding just enough artificial damping to smooth out those unwanted wiggles, those oscillations, without messing up the actual physics too much. It helps ensure the simulation behaves properly, respects things like entropy.
Okay, so a carefully tuned bit of friction to keep things smooth and physically plausible. What about accuracy, making sure the numbers are actually right?
Accuracy is obviously key. And the research really stresses the importance of those gradient correction operators we touched on earlier.
Right, the ones for completeness.
Exactly. They ensure the method can accurately calculate how things are changing locally, the gradients. This significantly boosts the overall accuracy. And they back this up with convergence studies.
Convergence studies.
These are tests where they run the same simulation multiple times, each time using more and more particles, refining the resolution. They check if the answer gets progressively closer to the known correct answer, or at least a very well-established benchmark.
And ideally, it should get closer.
Yes, ideally you want to see what's called second-order convergence for important variables like velocity or stress. It means if you double the number of particles, the error decreases by a factor of 4. It shows the method is behaving well.
Okay, rigorous testing, stabilization, corrections. Sounds like modern SPH is quite sophisticated. Now let's get to the fun part. All this theory is great, but what can SPH actually do? The sources had a ton of examples.
Yeah, the examples really show off its power and versatility. The thesis, for instance, simulates a bending column under pressure. They use this to test how well their new URL formulation works with different refinements.
Okay, bending something. What else?
They also simulate a tensile column stretching it, which is good for checking robustness and testing those anisotropic kernel ideas we discussed. And a twisting column, even with nearly incompressible materials, which is a tough test.
Bending, stretching, twisting. Sounds like they put it through its paces.
Definitely a virtual torture test. Then they did a really demanding punch test. Imagine pushing an indenter hard into a block of material. Lots of compression, potential for instability. They use this to check different ways of updating the kernels during deformation.
Okay, so handling compression too.
Yep. And an L-shaped block being twisted. This one was interesting because they used it specifically to check if the simulation conserved linear and angular momentum correctly, even when they added thermal effects, like heating.
Adding heat into the mix.
Yeah, and then the classic impact bar test, sometimes called a Taylor bar. You fire a metal cylinder at high speed into a rigid wall.
Ouch.
Exactly. It simulates the resulting plastic deformation, the mushrooming of the end, and importantly, the heat generated just from the impact itself, adiabatic heating.
Wow. That's pretty complex physics.
It is. They also did a necking bar simulation. That's where you pull a bar in tension until it starts to thin down in the middle, necking, and eventually breaks. Shows it can handle really large plastic strains.
Okay, so plasticity, large strains. What about actual breaking?
Fracture. Yes, that was a big focus too. They simulated dynamic fracture cracks starting and spreading quickly under load. They looked at different modes of cracking, mode I, and mixed mode.
How does SPH handle a crack forming?
That's one of the neat things. Because it's particle-based, particles can naturally separate. You don't have the headache of trying to redefine a mesh topology around a growing crack, which is a major challenge for mesh-based methods. SPH can model the separation more directly.
That sounds like a significant advantage for fracture mechanics.
It really is. And they kept exploring the thermal side, too. A thermal L-shaped block, again, checking momentum conservation with heat. A constrained punch block with holes, subject to both velocity and thermal loads. Even a shock wave propagating down a cable after a sudden force was applied.
Shockwaves too, man, this covers a lot.
It does. And for more fundamental validation, they used a swinging cube example to analyze convergence for different SPH formulations, and a tensile cube to test material models. Finally, even a gripper-like structure to show bending combined with thermoelastic effects.
Okay, I'm convinced. That's an incredibly broad range of applications. Elasticity, plasticity, heat, fracture, impact. SPH seems really adaptable.
That's the takeaway from the examples, for sure. Its strength lies in tackling these complex, often large deformation scenarios across different physics domains.
So given all this activity and potential, where does SPH go next? What's the future look like based on this research?
Well, several interesting directions pop out. For fracture, there's work on extending the simulation of cracks, like particle splitting techniques, into full 3D. And also using adaptive refinement.
Adaptive refinement.
Yeah, basically having the simulation automatically put more particles, more detail, only where it's needed most, like right at the tip of a growing crack to get higher accuracy, without making the whole simulation super expensive computationally.
Smart. More detail just where it counts.
Exactly. There's also a lot of interest in coupling SPH with other methods, particularly for fluid structure interaction, FSI.
FSI, like a wave hitting a dam.
Or maybe a shock wave in water causing a submerged structure to break. Imagine simulating that the fluid dynamics and the solid fracture happening together. SPH could be really valuable for the structure part, or even the fluid part in some cases.
Wow, yeah, that opens up huge possibility. Defense applications, maybe? Underwater explosions.
Could be. The research also hints at diverse fields like, yes, military science, but also medical applications. They mention the example of using shock waves, maybe simulated partly with SPH-like ideas, to break up kidney stones non-invasively.
Kidney stones. Okay, that's versatile.
And of course, just continually integrating more complex, realistic material models, capturing how real materials behave under extreme heat, high strain rates, damage accumulation, all that stuff.
It definitely sounds like a field that's still very much alive and pushing boundaries.
No doubt about it. Still lots of active research and development.
Okay, so as we wrap this up, let's distill it down. What are the absolute key takeaways from this deep dive into SPH?
I'd say the biggest things are, first, its meshless nature. That's fundamental. It gives it that inherent advantage for problems with massive deformations, free surfaces, interfaces, or fracture, where meshes struggle.
Right, the core benefit.
Second, its versatility. We saw examples covering elasticity, plasticity, thermomechanics, fracture. It can handle a really wide range of physics.
That's just fluids, despite the name hydrodynamics.
Exactly. Despite the name, it's widely used for solids. And third, the ongoing progress. Through things like improved Lagrangian formulations, stabilization techniques, corrections, the method is constantly getting more accurate and robust.
Okay, meshless advantage, versatility, ongoing improvement.
That pretty much sums up the strengths highlighted in these sources.
You know, the real aha moment for me, listening to all this, is just how this method, which is based on discrete particles, can so effectively simulate continuous materials.
Right. It's kind of counterintuitive.
Yeah. And not just simulate them, but handle these really extreme situations, impacts, fractures, where the continuous viewpoint tied to a mesh actually breaks down. It flips the script in a way.
It's a different way of looking at the physics, definitely, using discrete elements to capture the collective, continuous behavior.
So thinking about our listener, the learner,
Hmm.
understanding these SPH principles, even without mastering all the math, gives you a real insight into some advanced simulation tools being used out there, right?
Absolutely. It helps you appreciate the challenges in computational modeling and the clever solutions being developed. It's part of the modern toolkit in engineering and science.
So, okay, here's a final thought to chew on. With computing power constantly growing, how might these meshless methods like SPH totally revolutionize simulation and design, maybe in fields we haven't even thought of applying them to yet?
That's a great question. Or maybe flip it slightly. If we can simulate something as messy and seemingly continuous as material fracture using discrete particles, what other complex continuous phenomena out there might actually be better understood if we started looking at them through a discrete lens?
Interesting. Leaves you wondering. Well, if this deep dive has piqued your interest, remember those sources. The thesis and papers offer way more detail, but hopefully this gives you a solid foundation. Thanks for joining us on the deep dive.